this lecture, we will study the longitudinal beam dynamics. So far we studied mainly transverse beam dynamics. So this lecture concentrates on a new domain of the dynamics, that is longitudinal dynamics. Actually, we have accelerator coordinate system like this. This is the, you can say, design trajectory, and design trajectory itself has origin of coordinate system, and opposite to radius of curvature we generally take x-axis, and vertical to this we take y, and in the direction of beam propagation we take z. Now we were talking about the horizontal Betatron motion, means oscillations are taking place along the x-axis while the beam is moving along the z-axis. Means these oscillations were like this in this plane, like this here. And another motion was vertical Betatron motion, in which oscillations were along the vertical axis while beam was moving in the z-axis. So these motion was like this. These were the oscillations. Now we will talk about the third axis, that is the z. Now instead of talking about the z and z prime, we will take two new variables. What are those variables? We will see it. So for the dynamics which study about the Betatron motion is known as transverse beam dynamics, and now the dynamics, this transverse dynamics mainly governs by the arrangement of the magnets, that how we are arranging the magnets, where we are putting the quadrupole magnets, what is the strength of this, what is the length of the drift space, what kind of dipole magnet, and what is the angle, etc., and how we are arranging these magnets in making our optics, how the periodicity is there. These all things affects the transverse beam dynamics. Longitudinal beam dynamics mainly governs by energy manipulation of the particle, means how we are manipulating the energies of the particle. And when we talk about the energy, means we are talking about the RF cavity in which radio frequency electric field is confined, and that field is providing the energy to the particle. Whenever particle is traversing through that cavity, in a turn it gets energy. So longitudinal beam dynamics mainly governs by the RF cavity. So these are two basic realm of the beam dynamics. Some other classification of beam dynamics can also be there, that when we talk about single particle beam dynamics. Single particle beam dynamics means we are talking about trajectories of a single particle, or how the coordinates in 6 dimension, means x, x prime, y, y prime are the transverse coordinates, and other two variables which we talk about that will form the longitudinal coordinates. How these coordinates are evolving. In single particle beam dynamics, the presence of one particle doesn't affect the motion of the other particle in the beam. Means we have the collection of particles in the beam, but each particle sets its own trajectory without getting affected by the other particles of the beam. In reality, it is not so there, because all the particles are having charges. So when all particles move together, then they can affect the motion of each other via direct Coulomb repulsion or magnetic attraction, or via the vacuum chamber. Via the vacuum chamber means the charged particle induces image charges in the vacuum chamber, and those image charges can affect the other particles. So when one particle gets affected by the presence of the other particle, and we study those phenomena, then we are in the realm of the multi-particle beam dynamics or collective phenomena. In this course, we will mainly concentrate on the single particle beam dynamics under linear approximations. Even single particle beam dynamics can be broken down into two parts. One is the linear beam dynamics, and the other one is the non-linear beam dynamics. In last lecture, we have seen that introduction of the sextupole can lead to a non-linear motion for the particles. So that kind of motion where we are introducing non-linear terms in the Higgs equation and we are trying to solve that equation, and which can give rise to stable and unstable motion of the Petatron oscillations. That kind of studies are known as non-linear wave dynamics. So in this course we will not touch that kind of dynamics. We will restrict ourselves to linear approximation and mainly single particle wave dynamics. I will give one example of collective phenomena in the later lectures. Now let us suppose that this is the cavity, RF cavity, and this is the orbit in the synchrotron. Now a particle, when it crosses the RF cavity, it gets energy. And how much energy is needed? It is QV sin phi. V is the peak voltage and phi is the phase of the RF at the instant when particle is crossing the cavity. Now particle can take some time to cross the cavity and then phi may change during its course of motion inside the cavity. Means length of cavity has some impact on the motion. However, in this course we are not talking about that effect. Means we are taking RF cavity as a thin element. Means we are ignoring its length. Thin element. Like we did many times in transverse dynamics, we took quadrupole as a thin element. Here we are taking RF cavity as a thin element. Means it is a point where the particle is, when particle is crossing this point, it gets some energy. Now consider a particle which is exactly on the design orbit. Means it has x is equal to 0, x prime is equal to 0, y is equal to 0 and y prime is equal to 0. Means it is following the design trajectory. It is not exhibiting any synchrotron oscillation, Petatron oscillations. And it reaches exactly on the desired phase in the RF. Means there is a phase on which particle when arrives, it gets energy in such a way that its revolution time on the orbit is always an integer multiple of the time period of the radio frequency field. Means we can have t revolution is equal to HTI. So it gets energy such that this relation remains always true for this particle. Means this particle is always coming on the synchronous phase. And the radius of curvature of this particle when it passes through the magnetic field B is given by this relation R is equal to P upon QB. We have seen this relation many times. P is the momentum or design momentum, correct momentum of the particle. So this particle is known as synchronous particle. So we are characterizing this particle by two variables. One is how much energy it is getting and what is the phase in which it arrives at the RF cavity. So this is the correct phase. We say this is a synchronous phase and its energy which exactly follow the orbit or design orbit in the synchrotron, that is the correct energy. So this energy E of this particle and phase of this particle in the RF, these two makes a reference for us. Means in longitudinal dynamics we have two coordinates, one is the energy and one is the phase, and synchronous particles energy and phase make the reference. Means any particle which is deviated either in phase or in energy, we will study the motion of that particle with respect to this synchronous one. As we did in transverse dynamics, we studied the motion with respect to design trajectory. Means an ideal particle which is following exactly the design orbit, we talked the displacement and angle with respect to that trajectory in the transverse dynamics. In longitudinal dynamics, we will talk about how much energy is deviated from the synchronous one and how much phase is deviated from the synchronous phase. So E and phi makes the coordinate plane for studying the longitudinal dynamics. So now we have x, x prime, y, y prime. These are the coordinates in the transverse plane, and in longitudinal plane delta E means energy deviation from the synchronous particle, and delta phi, that is the how much phase is deviated from the synchronous particle. These 6 coordinates make the complete state of the particle. Now, how the synchrotron operates? Synchrotron operates on the basis that its orbit remains constant. In cyclotron, as the energy was increasing, orbit radius was increasing and particle was making a spiral path. Like this, there were d. When particle crosses the d, it gets energy and it's make a circular path here, and here again it crosses the d. So this time it will make a larger path because magnetic field which we are applying for guiding the particle is constant. So in this fashion, a spiral path is there in the cyclotron. The major problem with cyclotron was that if we want to increase the energy, first thing was that due to increase in gamma, synchronism may break, and other thing is that the size of the magnet becomes larger and larger, and making such large magnets is really a difficult job. So how we can reduce the size or aperture of these magnets? Instead of increasing the radius continuously, take some action so that radius remains constant. Means particle always revolve on the same orbit. So only this path has to be covered by the magnetic field. So this was major principle on which synchrotron works, and that's the way in which it reduces the requirement of the aperture of the magnets than this cyclotron. So in this case, as the energy, if we want to increase the energy, we increase the magnetic field also to keep the radius constant. So suppose P is the correct momentum, means momentum of the synchronous particle, then radius of curvature of this particle will be given by this relation. P is equal to QPR. P is the applied magnetic field. Now, as due to RF cavity, electric field imparts some energy to the particle, means it has changed the momentum of the particle. So we have certain dP by dt, and if we have dP by dt, then it will be QR dV by dt. Means we have to change the magnetic field also to keep the R constant. Means we have to ramp the magnetic field with energy. Now how much change in momentum will be there in one turn? So now this relation, you can see dP by dt is equal to QR dV by dt. So this is dP by dt. So in one turn, delta P for the one turn will be dP by dt into t revolution. So this will be QR B dot t revolution. Dot means d by dt. Whenever in this course I am using the dot, it means this is d by dt, and if I am using the prime, it means it is d by ds. So dB by dt has been written here as B dot. So QR B dot t revolution. Now t revolution can be written down as L by V, and because we are talking about some kind of closure path, may not be exactly circular, so we can take it as is equal to 2 pi and some average radius R upon V. So at the place of t, we have written this 2 pi some R mean, R average upon V. We can multiply V here. So we get V delta P one turn is equal to 2 pi R. This R is the bending radius and this R is the average radius of the orbit into dV by dt. Here you can see that V delta P is basically the energy gain, delta E. You can prove very easily that V delta P is delta E. You can take the relation E square is equal to C square P square plus M square C4. So if you take the change in energy, means you can take 2E dE is equal to C square 2P dE. These are constants, so differentiation will be 0 and this 2 will be cancelled out. This, so you can calculate dE is equal to C square P upon E dP. Now P itself is beta E by C. P itself is beta E by C. So by this you will get dE is equal to V dP, which is written here. So this is the energy. Now this energy gain is due to RF cavity. Means this energy gain V dP is QV sin phi. So these two values must be equal so that we will get the correct value of dV by dt for the keeping R constant. So this gives you what should be the synchronous phase corresponding to dB by dt in a synchrotron, so that particle will remain on the constant orbit. This is valid for the synchronous particle, means this phase is synchronous phase. Now one beautiful thing is here that you can see that if dB by dt is 0, synchronous phase becomes 0. Synchronous phase becomes 0 means here it is the time and this is the voltage in the cavity. So synchronous phase is 0 means particle is here or here. Means it is not catching any energy from the field. Means particle is revolving on the constant energy. This mode of operation of a synchrotron is known as storage mode. Means beam revolves in synchrotron at constant energy if we don't raise the field of the magnets. As we raise the field of the magnet B, synchronous phase phi changes and particle reaches to synchronous phase here, say, and it gets energy. So this mode of operation in which we ramp the magnetic field or change the magnetic field where the energy increases, we say this is the boosting mode of the synchrotron. So if you will see, if you will hear synchrotron or booster synchrotron, it means these are the synchrotron where the energy is ramped, energy is increased. And if you hear the names storage ring, accumulator ring, etc., then these are the synchrotrons made for the constant energy. Means beam is revolving in these synchrotrons at constant energy. So there are two modes of operation for this kind of machine. Any machine can be operated in both the modes if we have such kind of design. Means single accelerator can be operated in the booster mode as well as in storage mode. Or it can be a dedicated storage ring, means no boosting is possible. So such kind of designs are possible.